Is it on now? And am I audible?
Yeah,
This is good.
Very basic.
So, we are celebrating 100th year since the quantum theory was born. There has been a problem that has been born with the birth of quantum theory. That is, at that time we realized that everything in this universe is quantum.
Yeah.
And yet, we have an impression, even though our universe is quantum, that we live in a classical world. How come? This is a question I aim to address. How did the problem start? Well, you know the source. I'm going to start it off with textbook quantum theory postulates. Textbook is a good one, Dirac, and we know the source of the problem. Quantum superposition principle, mandated by the fact that states live in the Hilbert space, and unitarity, evolutions are just rotation in the Hilbert space. I should add here, there is one postulate which is not in Dirac, but which we know and love, and that is that state of a composite quantum system is a vector in the tensor product of Hilbert spaces. It's essential. This is where entanglement comes from. Statements 0, 1, and 2 are only math. We shuffle symbols, we stick in Hamiltonians, we calculate states, but there is no physics. Physics starts with number 3. Immediate repetition of a measurement yields the same outcome. This is known as non-demolition measurements. It's absolutely legal according to quantum theory. It's extremely expensive if you want to implement it. It has been done. Serge Roche, for example, in École Normale. 0 through 3 are considered non-controversial. 4 and 5, by contrast, are controversial. Outcomes of measurements are restricted to orthonormal states, eigenstates of the measured observable. So you can't use a measurement to find out what the state was, as you could classically. You're going to ask a question, you're going to get an answer, but it's going to destroy what was there before. And just one outcome is seen each time, collapse postulate. The last one, which is actually not as much in a quarrel with the top of the list, is probability, Born's rule. We all know why 4 clashes, right? Unitarity won't give you a single outcome. So without further ado, let me move on and tell you, so there are more than one idea that need to be stated in order to address everything. I shall focus just on one idea and remind you of another. The idea that I will focus on is the one that explains why do we perceive our quantum world, our quantum universe as classical world. In other words, we want to use the top of the list to explain the bottom of the list. Key idea that leads there is quantum Darwinism. It recognizes that observers such as us never interact directly with the systems they are interested in. Rather, they rely on spies. Environment is a spy. Systems and observers are based in the environment. So through decoherence, which extracts information by monitoring the systems, many records about the state of the system are imprinted on the environment. Fragments of the environment carry these records to where they may be accessed by observers. You are accessing my photon environment and my phonon environment. So this is not abstract. This is what's happening here right now. This information transfer can happen extremely rapidly, speed of light. many redundant copies are made. And you know they're redundant because there's, I think, 300 of you, and most of you would agree that I'm localized, for example. And this agreement is a source of objectivity. This is how objective classical reality emerges from the quantum substrate. Here is an incomplete list of colleagues from whom I have learned about this. Let me start by reminding you of something you probably know. It was discussed, however briefly, in this meeting. There is decoherence. Decoherence and environment-induced superselection or iSelection and preferred states. So what happens there? You start with a system and the environment. System is in a superposition. We will choose these initial states judiciously. It interacts with the environment to entangle. The interesting thing is that if you calculate density matrix of the system afterwards, if the interaction is the same and is the sort of interactions that we encounter in our world, you will end up with a density matrix which has the same set of states on the diagonal. In other words, if you happened to start in one of these states, interaction with the environment is not going to affect it. These stable states are pointer states. Einselection, environment-induced superselection, leads to pointer states. They are unaffected by the environment. The condition for that is that the observable, which has these states on the diagonal, commutes with the Hamiltonian of interaction. There are, it was a, I think, justified complaint that decoherence, which is by now, 45 years old at least, has not made it to textbooks. There are exceptions. For example, Weinberg's book on quantum mechanics does mention decoherence and does mention pointer states. So we are slowly getting there. There are also beautiful experiments which confirmed tenets of decoherence. Serge Haroche, Anton Zeilinger, Markus Arndt, Dave Wineland all contributed to this. So if we have decoherence, why do we need anything more? Decoherence eliminates superpositions. Is there a need for anything else? Well, decoherence leaves you with a density matrix, with a probability distribution. You know what's going to be on the diagonal, but you still would like to understand why in the end you just see a single outcome. This is where quantum Darwinism comes in. So what's the difference between the two? They look very similar. So here is decoherence. This is the same thing I had before. Entanglement between the system and the environment that leaves 0 and 1 unaffected. Environment finds out about the state of the system, you trace out the environment, you get a density matrix, always diagonal in the same states. What's quantum Darwinism? Essentially the same thing. The difference is that now you recognize that the environment is made up of many pieces, many photons, many air molecules. So, if you are entangled the same way, it's really the same thing, you have the possibility of extracting information about the system from the fragments of the environment. So, these subsystems are often very incomplete in what they know. A single photon won't tell you enough, but you can gather these subsystems of the environment into fragments, and fragments such as the photons which end up in your eye will tell you a lot. So the difference is in decoherence, environment could be monolithic. In quantum Darwinism, we recognize that there are many copies because there are many subsystems. So fragments of the environment can reveal the state of S. The other difference is in decoherence, you care about the state of the system. In quantum Darwinism, you take the state of the system, it's in the background. What you care about is what do you know or what you can extract about the system from the environment. So environment gets upgraded from a sort of trash can for inconvenient information to a communication channel. And it's an amplification. It's the fact that you spread the same information over many subsystems that is crucial. Let's do a very simple example. Here's my system in superposition. Here's my environment, just two subsystems. My interaction is controlled not. This is what's going to happen. This is a pure state. However, if I regard one of these subsystems as a fragment that I'm going to use to find out about the system and trace over the other, I'm going to get the density matrix, which is no longer pure. Here entropy is 0, here entropy is 1 bit. And I can either use one or the other to get the information about the system. The leftover is going to supply decoherence. I can also trace over two of these three, and I always will get this sort of density matrix. How do I quantify the information that the environment fragments know about the system? Well, a good quantity to use here is mutual information. Mutual information is entropy of one plus entropy of the other. What you don't know about one, what you don't know about the other, minus entropy, what you don't know about the two. So for example, if you have two copies of a book, if the two books are different, what you don't know about one and the other is the same as you don't know about both of them. If you have two identical copies, two copies of the same book, you know, the entropy, what you don't know about what's inside both of them, is as much as in either of them. How does it work in practice? Well, let's look at our very simple model. Here we have a system. We have just two-qubit environment. We find out about the state of the system immediately. It is revealed by a single fragment, single subsystem of the environment. If you get everything, then of course you are in trouble because this whole thing is entangled. So mutual information jumps up. Let's enlarge our environment. 1, 2, 3. Well, you get the information about the system from a single first fragment of the environment. Second fragment of the environment doesn't tell you anything more. You already knew from the first fragment what the second fragment was going to tell you. Again, well, I'll keep going like this till the end of the talk. You know what's going to happen here. 1, 2, 3. One tells me everything. The rest is redundant. This is what will happen if I have plenty of fragments. They will all know what's going to happen. The plot of mutual information is going to jump up of the first fragment to a level given by the entropy of the system and then stay there. And then jump up eventually when I get the whole pure state. What's important is to recognize that this flat part is a characteristic feature of what happens in decoherence, and we call it a classical plateau. It characterizes the way in which classical reality emerges out of quantum Darwinism. Redundancy in this case is simply the number of subsystems of the environment. This is how many times the information about the system is inscribed on the environment. This is an idealist version of a branching state. I'm borrowing language from Everett, but I'm not borrowing much past this language. And these sort of branching states appear when you deal with decoherence. In order to do this for more complicated situations, you need to have a more sophisticated definition of mutual information. That is, in order to do that, a convenient way of doing it is to employ von Neumann entropy in the formula for mutual information. It still measures information correlations between S and F, etc., etc. Let me introduce two important ideas, which is the key question: how much information about the system does a fragment F supply? So here I have fragments. How much does it supply? And redundancy. How many disjoint fragments supply almost all information about the system? Why don't I just say all? Well, the problem is that you have a realistic plot of mutual information. It's not going to go jump up to classical plateau. It's going to approach classical plateau slowly. Individual subsystems don't have perfect records. This, under sensible but not essential assumptions, is an anti-symmetric plot around this point. So you're going to get to where you have exactly HS at exactly half of the environment. You don't want to go there. You want to be happy with 10% less. So how does this work now? Well, suppose we have observers, we have photons which bounced off the system, we just intercept one fragment. This is not enough to make us happy. We intercept two fragments, well, still not enough. With three fragments, yes, we've hit this level. By the way, this quantity delta is important. It's known as information deficit, and it's clear why it's an information deficit. It's what you allow yourself, it's imperfection you allow yourself in acquiring information from the environment. In this case, redundancy would be equal to the total number of subsystems of the environment divided by how many subsystems you need to get almost complete information. There is a corresponding size of the fragment, and an important thing is you can now define redundancy using or employing the estimate of the size of the fragment, which is you want to get up to almost all missing classical information. So, decoherence, red plot. We go up very quickly. You hit what you want to, information deficit below HS, and you stay there for a long time. If you were to take a random state in the same Hilbert space, you would get a green plot. You find out almost nothing until you have almost half of the system and the whole thing, and then you would jump up very quickly to full information. This is it's been derived in another context by Don Page. The red one is the decoherence one, and that one we're going to focus on. So what we conclude at this point, almost all quantum states are non-redundant, the green curve. The redundant states we infer from observation are exceptional. How do we explain that? Special initial condition, we need low entropy. Special dynamics, decoherence, and we would like to understand exactly how these states come about in a reasonably realistic model. So here is a reasonably realistic model. Source of light, a superposition, dust particle, let us say, in superposition of two locations. So it's a cat state, irradiated, illuminated by photons. Amazingly enough, if you know scattering theory, and there seems to be almost no overlap between people who know quantum information and who know scattering theory, but I found one who does, you can solve that exactly. You get this beautiful formula. I will not let you enjoy it for much longer. I will just draw your attention to the fact that the only quantity which enters here is the decoherence factor, which means how much the off-diagonal elements of the density matrix of the system get suppressed by the environment. This is enough to give you mutual information. How does it look like? Here are the plots. If you are impatient and want to query the environment right away, after a fraction of a decoherence time, every little bit of the environment tells you a little bit more, and you never get to know everything. If you go to about 1 or 2 decoherence times, well, this begins to do something more interesting. But if you go to hundreds or thousands of decoherence times, the plot turns again angular. You jump up to a classical plateau and you stay there forever. So that means that even a small fraction of the environment is going to tell you with exquisite accuracy everything you wanted to know. If you have this curve, you can calculate redundancy. Notice that with light scattering, the number of photons scattered increases linearly with time. So redundancy increases linearly with time. Also notice that there is only a weak dependence on information deficit, which is good. This means it's a well-defined quantity. And it is linear in time, so as you go on, you get more and more records. And redundancy rate is proportional to a capped by decoherence rate. Okay, let me move on. So production of records necessarily decoheres. We knew that from decoherence theory. Reverse is not true. A very specific example, sun, 5,000 plus degrees Kelvin, photons bouncing off a dust grain in a superposition of two locations, exactly what we solved. We wait for just 1 microsecond. How many copies of where the dust grain is do we get? Well, an amazing 100 million. So redundancy increases very quickly. You are not surprised that without the sun, but with sort of mild light source, and with plenty of you still can get fairly accurate information about me, because this is what happens. Let us look a little bit more about the emergence of the information that is inscribed in different fragments of the environment. Here I bring back a Venn diagram. So here we have ignorance about the system, ignorance about the fragment of the environment, definition of mutual information that you have seen by now several times. And here is the same quantity, but defined in terms of conditional information. Conditional information is an interesting quantity to introduce because it tells you how much information about the system you are still missing after you have found out the state of the fragment. So HS is entropy of the system, HF is the entropy of the fragment. If you add the two and subtract the area of the whole thing, you get mutual information, but you can get the same thing by subtracting from the red stuff, the blue stuff, from the entropy of the system, what you still miss about the system after you found out from the fragment. Venn diagrams sometimes help, sometimes confuse. So if you are not particularly impressed at this point, do not despair. Let me go back to this plot. Classical plateau, decohering interaction, we have seen this. One thing that I want to emphasize here, that at this point we can calculate from this definition of information deficit that the conditional information is directly proportional to the information deficit. So it's basically what fraction of information about the system we are missing. This is going to be useful. So far we talked about what the fragments know about the environment, but we never get to measure the system. We just keep getting more fragments of the environment, more photons, or we meet other observers and exchange notes on what they have seen. And so the interesting thing is to find out where there is a consensus, whether the information that's communicated by all these sources of information leads to the same conclusion. And yes, it does, or at least here's the way to investigate it. Instead of asking about mutual information between the system and a fragment, you can ask for mutual information between two fragments of the environment. The formula is the same. HF plus HF prime, two non-overlapping fragments minus joint. I'm going to bring in a branching state. So here's a superposition. These are the pointer states of the system, stable under the environment. These are states of the first fragment, states of the second fragment, and these states have a record of pointer states. It may be imperfect. Then there is a rest of the environment, which we assume is large enough so it affects perfect decoherence. The rest of the environment knows exactly the pointer state of the system. Under this condition, you can calculate that several entropies, which superficially don't have to be equal to each other, are equal. There is entropy of the system, entropy of any fragment and the system is equal to the same thing. If you have this, you can also calculate that the mutual information between the system and a fragment is just 1 minus delta entropy of the system. This is a very useful formula, as this formula allows you to prove a theorem. It basically says that if fragments have enough information about the system, they must agree. And here is the extent to which they must agree. Mutual information between the two fragments is given by 1 minus information deficit of one fragment, minus information deficit of the other fragment, and actually plus the definition, plus the information deficit of two fragments taken together. It's a really cool formula because it shows that when you are approaching the plateau, that is, if fragments are good enough to tell you about what is there in the system, you end up with consensus. In other words, doesn't matter what fragment you ask about the state of the system, it will tell you the same thing. It is the collapse, in the sense that everything in the universe which connected with the system is going to tell you that. And I've extracted it here, by the way, without saying I'm going to measure these fragments. I have still pure branching state. I'm just calculating mutual entropies and conditional entropies. You can go a step further. By the way, here's the emphasis of this nice result. You can ask similar questions about the conditional entropy. And again, if conditional entropies between the system and fragments are small, then the conditional entropies between two fragments are also small. So here's sort of a direct evidence that they have to agree. In other words, if you know what's in one fragment, you can infer what's in the other fragment. This is how collapse occurs. Near the classical plateau, so small information deficits, fragments agree on the state of the system, and there is consensus. Let me do a brief recap, starting with the early transparency. The fact that we do not observe systems directly seems to be crucial to appreciating full consequences of decoherence. We knew that it produces density matrix, which is diagonal in pointer states. This is all good, but this is just a mixture. Quantum Darwinism tells you why you only can perceive states on the diagonals, the ones which are registered by the environment. Typical observers don't interact directly. We just use environment as a communication channel. Decoherence seems to be imprinting the information we are interested in, or maybe that's why we are interested in it, because it's being imprinted in the environment. Photons are very good information carriers. Many redundant copies, and sure, observers agree. Let me note that, and this is how objective reality comes about. Let me note that, as I said at the very beginning, this is just a fragment of what one would like to explain if one wants to have a proper explanation fitting for 100th birthday of quantum theory. What you would like to understand is not just how individual records arise, you would also want to understand where does Born rule come from. And this we can do. There are also interesting statements about irreversibility, which are different between quantum and classical. I did not have time, and it looks like I will not have time to go into this, but I can give you a reference. It's just appeared, Cambridge University Press, Decoherence and Quantum Darwinism. And as I'm stepping off the stage, let me thank Fumika, whose computer I'm using, because mine didn't have the right connections for this sort of setup, to produce this presentation. And she's going to give a poster session on a different, but also very interesting subject in which I am implicated on Thursday. Thank you for your attention.
All right, we have time for a few questions, right up front.
Right. That.
Yeah. Oh,
What's the for that?
nope, they're both off.
What's going on?
In my your state. Well, in that. Get off this gut. Get off about it, and I go. It's the city of well, you raise that about.
Perfect. Okay, so thank you very much for this amazing presentation. I just have seemed to miss one point, because you promised to explain why there will be just one outcome, and to me it seems like a beautiful dynamical explanation how consensus appears in the many worlds interpretation. So how do you get the one outcome?
So let me back. Am I on?
Mm-hmm.
Okay. Let me see if I can go back a little bit. So what you want to do is to view.
You bet.
There are two ways of viewing this state, right? This is a many-world state, absolutely. And if you put yourself in the role of one of the fragments, you will be going with Everett somewhere. However, what you can do is pose of this state the question that I thought, which is use information theoretic tools to tell you if the evidence in all of the fragments tells you about one state or many states. And if you do that, if you do information theoretic tools the way I done that, it basically they refuse that all of the fragments do the same thing. You don't know that thing. There is a beautiful complementarity here. So, there is stuff for average here, but there is also some on board. You don't know which state it is, but you know that there is one state that they agree on.
Yes.
You will destroy mutual information when you find out what the state collections are if you are. Right? So it's not that this is not a talk about interpretation. This is a talk about the information transfer. You can put on it interpretation, but in a sense, the explanation of how we perceive the quantum universe as classical is already there. What you may want to do is add something to your various real inner piece and use words like topology and epistemology, which I like. By the way, I think for this very reason, of these states as epicontic. They are undecided.
There are situations where they lack this information and we do that analysis in that spirit, but there's also nothing else in this universe that makes us apparata and the other things which are supposed to be classical. So with some leeway, political or mathematical licentia, you can go either average or bore. Then there are interpretations and use it in that context.
One more question.
Yes, you've been, and actually as we all would, this is such a big conference in an environment with very many of these systems that interact with the system and as our the communications channel to us. I would like to, I think your role is already pretty, allows to answer, what if you greatly restrict the number of photons? Is there a relation between the number of photons that have mediated in this channel and the amount of information about which the classical observers did reach consensus on? I think maybe there is a sort of some relation there. Yes, there is, right? And I think, I don't know if that convenient for us everywhere, but basically, I would like to get this is a good idea. Let me suggest that if you interact by means of n qubits, you'll be in the mediating parallel, you probably can get maybe something like n over 2 or n over 3 bits of classical bits of a consensus. It depends on that, right? I mean, if you are insisting on knowing exactly the whole information, then you will have to go all the way to the middle of the environment and you won't get there, right? So what we are utilizing the fact that this red curve rises very steeply. And we've seen how steeply it rises in the case of photons. And because of that, yes, you can fine-tune things so that you are exploring the beginning of this curve. And in fact, there are experiments done by now in several places where one can explore the beginning of the curve, approach the classical plateau. What's very tricky is to get here, because it gets in your way, even if you are extremely well isolated. So, depending on the level of agreement, deltas in your demand, you will have a certain number of observers, a certain number of photons that you will. Good.
All right, so Jack has a quick announcement, but while I'm handing over the microphone, let's thank all the speakers.